Thanks everyone for coming. Today we're going to have David Redish. He's a neuroscientist here at the U, and he's going to be talking about ways in which neuroscience can come into economics and how economists can use some of the tools from neuroscience and bring it into thinking about the way that we do our theory and the way that we do our modeling. So let's welcome David.
So what I want to do today, thank you everybody for coming. Thank you everybody online. Ryan will be monitoring the chat. So if you have questions, please either raise your hand here or mention in the chat, and Ryan will bring it up and we'll repeat it so that it goes on to whatever recording this is. What I want to do today is I want to make two cases. I want to make the first case, which is that at this point, to do economics correctly, given that people are actually interested in economics as economists, you need to know the neuroscience. That's the first thing I want to try to convince you of. And second, I want to convince you it's not that hard and it's not that scary, and you can actually do it relatively easily. Today, I am going to give what is hopefully enough depth that people will actually believe there is full depth here, but I'm going to give a relatively superficial showing of it because I only have an hour to do this. For the graduate students, if any graduate students are interested, I teach a class on this called Mind and Brain, which has a graduate designation of Neuroscience 5505. It's a both undergrad and grad class, but graduate students can take it for graduate credit. And that's a full semester-long class that goes into all the depth with all the equations and everything like that. All right, I want to start off with 2 points that I think are relatively not controversial, but have consequences that are usually not appreciated. The first is, try that again. The first is that any normative model is only compatible with some process assumptions. That is, if you buy into a statement about maximizing under some conditions, that will only work given certain process assumptions. And in parallel, any process model has normative consequences. To say I'm going to optimize assumes that you are only going to be able to optimize under some conditions. So if you have a process, that process can limit the normative model. And when we talk about this in a philosophy of science language, it's usually talked in David Marr's 3 levels of what he called computational, algorithmic, and implementational. And the idea is that the computational is the large scale, what's the goal we're trying to do? Addition, for example. And in economics, I believe this, correct me if I'm wrong, I believe this is what economists usually call as-if models. Then you have what Marr would call the algorithmic level, which is the process that's going on at a descriptive component. And then finally, there's the implementational or mechanistic final component of how things are actually built. And behavioral economics has tried to start at this computational level and gone down to make guesses about the process model because normative observations have limited process models they can get to. I've stopped this at the very tip of the algorithmic level here because there are a lot of processes that can create an as-if observation, and this is very hard to do. What neuroeconomics says is let's start instead at this bottom implementational level and work our way up. And what I'm going to show you today is that we can in fact work our way all the way up to as-if computational, practical, real-world consequences. And this is something that has only really developed in the last couple of decades in neuroscience. So for those of you who weren't doing this 30 years ago, we weren't ready. But I want to argue we are ready today. And the big key to this whole story is that representation, how you store the data, limits the computations that you can do. And therefore, these levels depend on the lower levels. So this is what I'm basically going to do today. Now, before I get there, I want to start off and punt. I want to shut down and avoid the discussion of that's not an economic decision. Because, and I'm not going to do this right now because it would take me about an hour, but if people want, I'm very happy to talk about this offline or afterwards, etc. Essentially, you cannot draw a true line that separates economic, what people often like to call economic, quote unquote, decisions from other decisions. And instead, to be philosophically consistent, what you need to do is define decision-making as action selection. And yes, okay, we'll take freshman philosophy as well. Not acting is acting. So if you can take an action and you don't take an action, we'll count that as a decision as well. And this works if you're a rat deciding where food is buried, a monkey deciding where to look its eyes, a rat running on a maze. I get the video, of course. It also works for basic consumer purchases of how much sugar do you want, are you willing to pay through this vending machine? You're taking an action of putting money into the vending machine and pushing some buttons. It works if you're deciding whether or not to go gambling. Eventually, when you're gambling, you're rolling dice or you're pulling a lever. You're taking an action to go gambling. It works for any sort of drug question, whether you are injecting something in your veins or smoking it or taking a pill, you are taking an action. Don't do drugs. It works if you're taking a big action like buying a house. Eventually, you're taking the keys, or buying or selling stocks. You're taking actions to take this achievement. And my favorite example is getting married, where you and your spouse stand in front of the community and say what's called a speech act to say, I do. And now the community agrees to treat you differently. And if we define all of these as decision-making, now we have a different question, which I'm going to argue is philosophically stable, which is, what was the information process that led you to take that action? And when we ask the language in this question, now we can get from neuroscience to economics. What we're going to find is that decisions are basically computations of information about the past, we call that memory, about the present, we call that perception, and about the future, we call that motivation. And it's going to essentially be a computational process of these three components in some complex way. When you do this, what you find is a new microeconomic model. And this is going to be my main kind of first part of the talk. Spend about 20 minutes on this, laying out what I believe is the current neuroscience tells us is the correct microeconomic model to start from. And in the last 20 minutes, I'll give you 3 examples where this actually has concrete consequences for us to study. Jay?
Quick question, David. In a lot of the work in environmental economics, we're interested in what it's worth to people like to preserve a species.
Right.
And that often involves a survey,
Okay.
carefully done, in which people respond with opinions.
Right.
But is that an action?
So the question is taking a survey an action?
Yeah.
And there's 2 answers to this. One is, yes, circling a thing or clicking a button is an action. And so from a kind of first principles, we can call it that. And in fact, one of the very important points is I think of this from the medical perspective, although I'm not a doctor, I spend a lot of time working with psychiatry, for example. And saying I feel pain does not mean you feel pain. It means you've taken the action of stating I feel pain. So for example, if you feel pain in your left arm and the doctor starts testing your arm, that's a bad doctor, because pain in your left arm is actually almost certainly a heart problem, right? So one has to separate the action of I've circled this number from what it means, right? That's one answer. The other answer is that this can be a piece of a way of trying to probe, to some limited extent of how successful it is a debate, but a way of probing the representation that is used for the action of deciding to vote in a certain way to save a forest, or to act in a certain way to save a forest. And one of the things that starts to get complicated is if I decide to take the action, but then I'm prevented from that action at some point, where do we want to go with it? And at some level, I don't think we need to get into that level of detail, because we're still talking about what was the information process that led the person to take that survey choice. Does that make sense? Yep. Thank you. That's a good question. So when we look at this, we basically are going to come to this idea that there are 4, at least, there's some evidence, there may be a couple of others, but there's at least 4 very clear action selection processes, which I will go through in a minute. But before I go there, I want to reject a couple of classic dual process dichotomies. Now, for most of the people here, being economists, you're probably not living in the psychology dichotomy, but there's a classic psychology dichotomy of Pavlovian conditioning, where the animal does not have to take an action to get its reward, and an instrumental conditioning where the animal has to take the action. So in Pavlovian conditioning, a cue comes on, a reward shows up, and the animal responds to it. The action is somehow in response to this reward. In instrumental conditioning, the cue comes on, the animal takes an action, does something like push a lever, and that reveals the reward. The problem with this, and the reason I want to reject it, the reason I like to start with this is fundamentally the wrong point of view. This is the experimenter's point of view, not the subject's point of view. And what I want us to all do now is to think of these questions from the subject's perspective. What is the internal information process that the subject is doing? And that's the key question here. Probably more relevant to economists here is System 1 and System 2, which of course was popularized by Daniel Kahneman over the last many years. And in this, you basically have what's called a deliberative or rational System 2, and everything else is shoved into this heuristic set of biases called System 1. This is, in fact, actually built on 1960s psychology, which I'll reject on the next slide. But let's reject this one here for a couple of reasons. First of all, there are more than two systems, and these systems are at least as different from each other as they are from deliberative and planning. Second, System 1 lumps all of these computational considerations, some of which are clearly decisions, and some of which are other things which have decision consequences, like perception. Perception is a process, and that has consequences. The mechanisms of perception, we will see, will have consequences for decision, but that's fundamentally different from learning a habit. And third, deliberation also has computational limitations. It is not rational in the kind of classical economic sense. Now, so we're going to reject this. In fact, what we're going to reject is we're going to reject the overall idea of this classical 1960s psychology that there is a human cognitive system trying to control a non-human animal one. And here's a bunch of popular science books that all try to sell this story. Actually, the best description of this is the science fiction novel Dune, which is, of course, all about sifting for humans to control their animal impulses. So you get like, fear is the mind killer. This is exactly what these people are talking about. I believe Frank Herbert was actually a psych undergrad, and that's where he got it from. We're going to reject it. I will point out that this is, in fact, very old. This is at least to ancient Greek, right? Plato talks about controlling a wild horse and a thoughtful horse. This is in the Ramayana, so I'm pretty sure it's actually pre-Greek. It's Indo-European in some sense. This is Augustine's City of God and City of Man. This is Freud's Ego and Superego and Id. This is The Horse and Rider from people like Jonathan Haidt. And I want to reject this because, first of all, there are more than two systems. Second, all of these systems are useful. It is not that there is a better cognitive system and a worse animal one. Each of these systems is optimized for different situations, and they are therefore going to be needed in different places. So we're going to reject this as well. Henry?
Question with Freud in particular, isn't he more than a dual process theory insofar as there's three components?
Yes, and in fact, Plato has a third charioteer.
Yes.
Which is a different issue, and that's the issue of what do you do when you have all these multiple systems, and who controls when they get into conflict. So if people haven't heard of him, one of my favorite science books is a pair of books by a guy named Stuart Firestein. One's called Ignorance, and the second is called Failure. They're really phenomenal kind of, what is science and how does science work books. Ignorance says the goal of science is to find new questions. So he talks about your ignorance question. What was the question that you didn't know was a question until you did your science? My ignorance question is, how do you reconcile when you have multiple decision systems that conflict with each other? We actually don't know that answer. That is, in fact, something that we are working on in neuroscience today. But that's an interesting question, and in fact, there's a lot of economic discussions happening on that right now. So, the new microeconomic model is that you are all of these systems and that we need to think about them computationally. That's going to be my push. So let's go through each of these really quick and see kind of how do they represent information, and then we'll see what some of these consequences are. So reflexes are actions, right? They are pre-wired responses to stimuli. They're learned over evolutionary time. Basically, your ancestors had these reflexes, they survived and procreated, therefore you have these reflexes, and they are things like throwing out your arms when you fall down so you don't break your nose, shivering when you're cold. Very importantly, we know the neurophysiology of it. You don't need to know it, but we do, and each of these systems turns out to access a completely different neural circuit. And the way a lot of these were found is people were found with damage to different neural circuits, which would shift people in these decision systems. So this is a spinal cord system. The problem with reflexes is very limited in what you can learn and how flexible it is. So we get to kind of the first level of flexibility in what I'm going to call instinctual systems. But to be honest, much of the field calls Pavlovian. I'm not a fan of this word because it confuses the psychologists, because we already had that Pavlovian distinction, but it is what Pavlov's dogs were doing. Basically, what this is a limited set of species important actions that you learn when to release. So for example, the dog gets some food, it salivates in response to the food, and then a bell is rung often before the food, and the dog starts to salivate to the bell. This works through a neural circuit based on a structure called the amygdala. Again, it's a different neural circuit. One of the things that surprised neuroscientists over the last 20 years or so is that it turns out that yes, instinctual things are the basic circuits of like fight and flight, feeding and things like that. But it turns out a huge amount of human social interactions are based on this circuit. Laughing with your friends is based on this circuit. And so this gives you interesting processes where we can see consequences. So this circuit is only about immediate rewards. This provides an excess valuation to immediate options. And so how many people have actually heard of the marshmallow test? Okay, some. So the marshmallow test is a wonderful, if you haven't, go find the videos because they are beyond wonderful. There are lots on YouTube and Vimeo and things like that. And basically you take a young child, say 3, 4, 5, put them in a bare room with a plate and a marshmallow. And you say, if this marshmallow is still here when I come back, I'll give you a second marshmallow. And then you walk out of the room. And the kids desperately try not to eat the marshmallow, because if they eat the marshmallow, they don't get the second one. But it's really hard. And it is just beyond wonderful to watch, right? But this excess valuation comes from that instinctual Pavlovian system. The problem with both reflexes and instinctual systems is they have limited repertoires of actions. You can run from the lion, but you can't do jumping jacks in front of the bear, right? What you can do is run from the bear, which, as I understand it, is the wrong thing to do. So that leads us to two additional systems, one of which I'm going to call deliberation or planning. And deliberation and planning really is a search and evaluate process. What it actually does is it specifically goes through and imagines future outcomes. It says, if I'm trying to decide about where I'm going to go for vacation, I'm going to imagine what would it be like to go skiing in Colorado? What would it be like to go to Chichen Itza in Mexico? And very importantly, the sequence is you imagine Colorado, you imagine skiing, you imagine the cold, you imagine going up the chairlift, you imagine is everybody on the same ski level. And then separately, you imagine Chichen Itza, and you imagine it's hot, you imagine you need a passport, you imagine that you need to speak Spanish, you wonder, is it going to be crowded, right? You don't ski down the slope of Chichen Itza and let its quantum settle out. And so this is an actual search and evaluate process and depends on a whole very complex neural circuit that we have a lot of access to. Things like the hippocampus and the prefrontal cortex and the nucleus accumbens core and other things like that. notice that I've defined this computationally. And that means that I've reified this process and I can look for it in a non-human animal. In fact, one of the things that kind of made my lab its name in the early days was we discovered that rats really do deliberate over choices. They will occasionally come to a choice, stop, and imagine, what if I go left, what if I go right? If I go left, there's cherry flavored food pellets. If I go right, there's banana flavored food pellets. Do I want cherry? Do I want banana? What am I gonna do? And they really do imagine that outcome. The problem with this circuit, with this system, with deliberation, is that it's slow. And so if you're gonna do something fast, like hit a baseball or land a triple axle jump, if you want fast or reliable, you've got to have a different system. And this we call the procedural system, which is based on cortical perception and then releasing a well-practiced action in the dorsolateral striatum. And what this system is basically doing is taking a sequence of state action pairs and turning it into an action chain. So when people talk about these systems, they usually talk about it in this language, from Pavlovian or instinctual systems to slightly more complex habit systems to much more complex cognitive planning systems. The problem with this is this doesn't really allow you to kind of understand how these interact with each other. And we realized actually in a review paper we wrote with, this is Amber McLaughlin, who was a postbac, and Jeff Deal, who was a postdoc at the time. And we wrote a paper over the pandemic. This was our pandemic thinking. And we realized that if you restructure this in this order, that is Pavlovian to cognitive to procedural, what you're actually talking about is increasing regularity in the environment. The Pavlovian system works. You run from the lion the first time. You don't need to know anything about the environment. That's a lion. You can run from it. The cognitive system needs a stable environment, but the actions don't have to be stable. I can know where Root Hall is, but I don't have to go there until it's time to actually go give a lecture there. Procedural systems require both the world and the actions within them to be stable. So this gives us overrides as regularities are recognized, and what I like to think of as pop-up in times of change. The cognitive system can come in and say, okay, I know we practice this, but the world's different. We need to do something different. Kind of let's do something different here. And the instinctual system will go, emergency, emergency, I need control right now. Yeah.
Our base consumer model of consumer behavior involves two halves of a scissors. People's preferences,
Yep.
which I think you're describing here somehow.
We'll get to we can talk preferences. Go ahead.
And the constraint that limits their choice.
Right.
So where is the constraint here?
So first of all three of these have preferences. And one of the things I'm going to show you is they don't necessarily match. And in fact, a lot of the issue that economics desperately needs to pull in, and one of the reasons you need these systems, is that a lot of the complexity of conditions changing preferences because it's changing decision systems. So to the extent to which preferences are describable as a unified whole or need to be thought of separately is something that in fact is being discussed and is a real place for neuroeconomic interaction and discussion. And then the other is the constraints change depending on how each of these systems have learned how to handle this environment. And so that learning is going to depend on those constraints and it's going to give you those constraints. Right.
I think Jay sparked an idea, but I don't want to derail you. So I was going to
Okay.
ask, are you going to talk at all about like the sociological aspect of economics? So thinking about the firm or the government, like when decision making and optimization is at like.
Yes, at the very end, I'm going to mention the beginnings of it. I don't. The short answer is that's a space to go work on, right? Because right now, organizational psychology, firm-based, is that the word I want to use for economics? But the economics of firms and communities is not based on this neuroscience. And what I'm going to show at the end is actually in microfinance, at least, success of microfinance has depended, well, actually, I tended to take that off for time, but I'll show some beginnings of how to do that. And we have some evidence that at least in things like microfinance, the success of microfinance enterprises has been because of they interact with these systems, not for the economic reasons that they originally thought. I'll show this on more individual levels, but we'll see. So one of the things I want to point out is that actually this mechanistic process has consequences. The procedural system is a highly consistent system. It only shows up when you are doing the same actions in the same environments. But the deliberation system is a sampling process. It's literally running this depth first sequence. And so just like the sampling economic models, it's inconsistent. And in fact, the more you make somebody say list pros and cons, the more you push them into this system. So the more you drive somebody to what should be system 2, quote unquote, rational, quote unquote, the more inconsistent you are going to make them, which is the opposite of what economics generally predicts. So this set of systems is the beginning of the story. I want to point out that we actually, in the neuroscience world, know how memory is stored. We know the mechanisms in the process of memory, that it works by a recall of content, that it's not veridical. We know that sensory cues is a process of inference, that it works by categorizing situations, and what expertise is learning what dimensions you need to pay attention to correctly infer things. That has consequence. We know that motivation is a memory process of its own. One second. And anybody who has eaten food, 6 hours later been throwing up and never wanting that food again, knows that your preferences are malleable, and they're malleable by a learning system happening in the motivation system, which again, we know a lot about. Finally, we've been talking about action selection as buy stocks, walk from point A to point B, but that's actually a motor process. When I walk, I have to put my foot down and pick it up, and there's a whole process there. We again know a lot about how that works. To what extent that's going to have consequences depends on the specific questions. Ryan, it sounds like there's a chat question.
Yu-Chen has a question and he's going to unmute and ask.
Okay.
Thank you so much. My question actually comes in 2 parts. The first part, I want to say a recent review on the marshmallow test argues that the more patient kids in the test are more likely
Hey, Yu-Chen.
from richer families. So marshmallow is less a rare treat to these kids. So this leads to my actual question. There are unobservables or confounders in play when we analyze the decision process. In the language of economists, we say there are unobservables and confounders. If this is also a concern in neuroscience, like how do neuroscientists address this issue?
Right. So question. The beginning of the question was to point out that people had originally thought the marshmallow test reflected some sort of cognitive abilities. And now there's evidence that there's a lot of socioeconomic components that were in there originally. You'll notice I didn't bring in cognitive abilities. I didn't bring in a claim that the marshmallow was driving one way or the other. I wasn't suggesting abilities. I'm not suggesting interpretations about doing better or doing worse, right? The mechanism of the marshmallow test is pretty solid. And so then the second part of the question is, how do we handle the unobservables? And the big answer is you open up the black box, right? One of the big problems with old school psychology, going back to Skinner, with economics in a lot of its language, is there's an assumption that we can't look inside the black box because somehow either we don't want to, or we can't, or we don't know the mechanism. I'm telling you, it's all there. We can look inside this black box. We have fMRI technologies, and don't get trapped in the fMRI is blood flow. Don't get trapped in the fMRI is, limited, or people who are trying to look for blobology. There's good fMRI studies, right? We know that you can actually, my lab puts electrodes in the brains of non-human animals. And when I say a rat is imagining the future, I'm not being hypothetical, right? I'm stating that as a literal fact. That rat imagines the future. In fact, I have more evidence that a rat imagines the future than any of you do, because I haven't actually opened your black box and I haven't shoved electrodes in your head, right? Now, there are cases where you can put electrodes in human heads. Tends to be in clinical settings, but often these patients are sitting there bored in the hospital with, stuck in the head, stuck electrodes, and you come say, would you like to play our cognitive game for a while? And they're like, yes, please, please, anything but that reality television they've got playing, right? So the answer to the unobservables, there's always unobservables in science. This is how science works. We try to explain the unobservables. But as technology moves forward, we can open up and observe things that were thought to be unobservable. So a lot of what is going on in neuroscience is that we are, I believe, being able to observe these unobservables. Yes.
And just so I'm clear, because this is new to me, when you say the rat is deliberating, you're basing that on where in the brain you're getting activation?
No.
Like that. How do you?
Right. So one of the breakthroughs in neuroscience comes about in the late 80s, early 90s, is it turns out that memory and imagination is a reactivation of neural systems. So when you imagine a face, there's some signal, presumably in your prefrontal cortex, that says we're in simulation mode, we're imagining. But the face area of your cortex, located about here, that represents when I look at your face and I process, that's a face, and that's, that's your face and not, say, somebody else's face, right? That part of the brain, it becomes active, and in fact, the neurons rematch the pattern that they were when I saw your face the first time. And because we know that from humans, we can now go into rats, identify, in our case, parts of the brain that represent where they are in space, and observe that at certain moments, those parts of the brain don't represent where they are. They represent a sequence running from where they are all the way forward to the goal. And then on the next moment, all the way forward to a different goal, right? So it's because, and that actually was the computer scientists coming in the 1990s saying, here's how you do decoding. Here's how you think about representation. And so we now can do that kind of inference. We can, I like to do, when I'm doing like a popular science thing, like if I'm like in an improv troupe and they say, everybody, what do you do, right? I like to say, I read rats' minds and I listen to their dreams, right? Which everybody kind of goes, whoa, wait, what? Right? I was in one improv group and I did that. And then the person who'd invited me goes, he's not kidding. So yeah, so that's the mechanism, right? And this is what I mean by opening the black box. You say like, well, we can't really see deliberation. We're going to infer it by taking longer in the reaction time or whatever. No, I actually can go in and look, and I can tell you that rat at that moment is deliberating over choices.
And so you can tell that the child is not deliberating over eating the marshmallow or not, but they're responding.
Well,
You said it was a different process.
So what you find and to be honest, I don't know that this has been done with the marshmallow test directly, but it's been done with other similar things. Those kind of immediate, like, the sugar just makes me want to eat it, is driven by the neural circuits that we know are part of that instinctual system. That is, those are the circuits that are active in those moments. Whereas I have two tokens, I have a token, I have a little token, and I could use that token to go over there and buy myself a marshmallow. But if I can sit quietly, another token will show up and I can take those two tokens and buy two marshmallows. That is part of the deliberative planning system circuitry. And that's why it's easier to wait for two tokens than it is to wait for two marshmallows. Does that make sense? Cool.
This is a small question,
Mhm.
push back, it's gonna be answered. A big component I think of when I think of utility is exchange, right? So the utile being this imaginary thing.
Right.
And then that becoming currency. In this setting, when you're looking into the brain, are people able to abstract out like this is some currency?
We don't know.
Okay.
So that is in fact a point of high contention. So the question is there a common currency in the brain that everything gets translated into for comparison? And in full neuroeconomics, to be fair to all the other neuroeconomists out there, there are many people who believe, yes, they can find it. There are other people who believe, no, what you have is different systems with their own currencies, some of which match utility in certain ways, some of which don't. That is a point of high debate right now. My take is no, and I'm going to show you a couple of examples why I think it's not, and why I think it's always been not. And economists have known since the 1960s that it's not. So I think I'm going to skip the memory stuff in the interest of time. I'm just going to point out that, and then I'm going to jump to some examples. I'm going to skip this first one. This first example was me showing that you can show economic decisions in non-human animals. But I can come back to it if people want, but in the interest of time, I'm going to jump straight to contingency management, which I think is particularly for economists, the example to be thinking about, because this is a case where we've really seen the consequences of this discussion we're having.
David, just quickly, the first one is you're finding that rats are
Yes. So
susceptible to the sunk cost
Yes.
fallacy?
basically mice, rats, and humans. I mean, if you want me to go through it, I will.
Well, I don't want to deter you, but
Do people want me to go through this one? Because what we find is basically mice, rats, and humans are sensitive to sunk cost. And we have parallel tasks. But it's more about the fact that that's a surprise that mice and rats are, than it is, really getting the economics of, it's using an economic tool to get to these questions more than the neuroscience to get to economics. What would people prefer? People in the room get to vote.
oh, yes.
Okay, all right, we'll do this one too. I'm happy to do this one. We may run a little over, given timing. So basically, this is a task we've been working on for a while, and the idea is that we have rats and mice running on a task we call restaurant row. So the rats and the mice come up through this central track. I bet I can do a laser pointer here. Let me see. Here we go. So the rats and mice come up. Can people see the laser pointer online now? So the rats and mice come up through this central track, come into what we call the offer zone, and they hear a tone. The pitch of the tone will tell them how long is the delay before food. And they can either skip that deal and go and try their luck at the next restaurant, or they can take that deal and enter into what we call the wait zone, where the tone counts down. So it would be enter into the zone, 3 seconds, 3 seconds, 3 seconds, 3 seconds, take the deal, 3, 2, 1, food. Now, while they're in the wait zone, they can also quit and say, forget it, I didn't want to wait that long, and they can then go try their luck at the next restaurant. Importantly, the deals are random, 1 to 30 seconds on entering the restaurant. They don't know what it is till they cross the offer zone line. And they have a limited amount of time to get their food for the day, which means they have a time budget. And they are spending time, and time spent waiting for plain food is time you can't spend waiting for great food. Okay. Now, humans, we didn't want to, make the humans work for food. So instead, what we realized is that we can do exactly the same thing with videos. So the human comes and opens a web browser, and they get a download bar. And the question is, are you willing to wait for the 30-second download bar to watch your kitten video? Or do you want to try your luck at the ballroom dance restaurant next door? Does that make sense? Now, see if does this turn it off? Yes. So every animal we've ever run, whether it be a mouse, a rat, an undergrad, a human, whatever, have preferences. And these preferences are revealed to us by their willingness to wait for food. So, for example, this rat, or this mouse rather, will wait a long time for banana, but very little time for grape. On the bottom here, we have the circles or delays that they skip. The x-axis is delay. And on the top, we have the circles of where they took the deal. The filled circles are ones where they quit. So this mouse will wait up to about 15 seconds for banana, but only about 4 seconds for grape. This rat likes everything, but likes plain the best. This human likes kitten videos and a bite fail accidents videos where people fall off roofs and things like that. They hate the landscapes. Right? Everybody has revealed preferences. And actually coming to Jay's question earlier about surveys, human preferences match both their verbal ordering of which ones they like and their ratings of the videos themselves, and their their ranking of the videos. So all of that tends to match, turns out.
Is there a time constraint on the people?
Yes, they have a certain time limit, and there's a clock. No, actually, they get satiated, in fact. But you have a limited time and they're sitting in a boring room, and so they want to watch videos. We've run this online as well, and I don't have time to go through all the details of it. It's a whole other, I mean, I have a whole hour-long talk on this. But online, there are some people who are inverted and actually prefer longer delays, and we're pretty sure they're watching their phones. But most people actually play the game correctly. So the way we operationalize sunk cost in this is we're going to take a moment where a person takes or a subject takes a certain deal, and then somewhere in that waiting time, we're going to ask, what's the probability that they finish out the wait? So imagine that at this analysis point, there's been 5 seconds invested and there's 10 seconds to go. The question is, are they going to wait out that 10 seconds? What's the probability they finish waiting out that 10 seconds? And we're going to compare that to taking a different deal where they have a longer time invested, but the future is identical. Notice, in these cases, the future is completely identical. The only thing that's different is the past. And what we find here, and we're going to look for, is an escalation of commitment between these two conditions. We also see an escalation of commitment as you get closer to the reward, but there's a few things. Sunk costs can give you that, but other things can give you that as well. So this is a little complicated, this plot, but let me take you through it. What we have here is the rat entering into the wait zone. And we're going to take all the trials where they entered with 30 seconds to go and say, what's the probability that they stuck out that full 30 seconds? And the answer is not many. You can do this for all different delays, and we get kind of what's effectively a psychophysics curve. And then this is the set of probability of waiting out the delay, given that they've waited 1 second. So these 2 points are the same data. This is just the difference between before and in black before and in green after they've waited 1 second. You can see there's a dramatic increase in the probability of waiting out the delay. More importantly, these 2 points both have 29 seconds to go. In the black dot, you've spent 0 seconds of sunk cost. In the green dot, you've spent 1 second of sunk cost. And you can see there's a massive difference in your willingness to wait out the delay as a function of having already spent 1 second. And we can fit this with lines. We do more modern things now. This is from 2018, but we did lines because the human data was noisy. But basically, the longer that you have waited, the more likely you are to wait out. And it turns out you are sensitive to the time that you've already spent. And this is a sensitivity to sunk costs. Now, the cool thing about this is we can do exactly the same analysis when the animals enter about the time spent in the offer zone. So do they spend very little time in the offer zone, or do they spend a lot of time in the offer zone? Are they sensitive to sunk costs that they spent in the offer zone? And the answer is not at all. Sunk costs do not accrue until the animal commits to its choice. And it turns out this is something in the human literature called crossing the Rubicon, and is seen in the task engagement literature. Before people engage in the task, they're very, very willing to say, forget it. But once they're engaged in the task, quitting is hard. And I'm gonna show this video because I just love this video. But this is a mouse. It's gonna come up. It's gonna come up here. This is gonna enter the offer zone. This is the offer zone right here. It's going to enter the offer zone. You're going to see it dither and deliberate for a long time and then hesitate. This is the wait zone right here. It's going to hesitate before crossing the wait zone, making it very clear that it knows that it wants to be sure that it crosses the wait zone. And that mouse knows that crossing the wait zone is a Rubicon. It's going to get stuck. And in fact, what happens is all subjects learn to dither and deliberate in the offer zone to avoid that sunk cost in the wait zone. And the reason that this is particularly interesting is subsequent work has determined that in the offer zone, the animals are using these planning systems. They're using what's next systems, what's the future systems. And in the wait zone, they're using these instinctual systems. And the neural circuits, we can actually manipulate, because we have neuroscience techniques, we can literally manipulate the neural circuits to change their ability and their sensitivity to sunk costs in these wait zones. Okay.
So it seems now that they are susceptible, at least they're sensitive to a prospective sunk cost.
No,
When they make it.
they are aware, they are willing to pre-commit to avoid the sunk costs. So they're sensitive to the sunk costs in the wait zone. And they're willing to pre-commit to avoid getting into that mistake. And yes, it is in fact a pre-commitment matching economic questions of pre-commitment. So now I want to move on to contingency management and talk about contingency management is a great example of something where this is an economic story that turns out to depend on the neuroscience. And the neuroscience is going to allow us to make this economic treatment better. So contingency management is pay people not to take drugs. You basically come in, you prove that you haven't used this drug you're trying to avoid for a week. Maybe you give them a urine sample, and so you can prove you don't have the metabolites or whatever it is, and then you get a small reward. And the theory and the explanation of contingency management, it is, by the way, one of the best treatments for drug addiction that we have right now. And the way that it's always talked about is that it's about opportunity costs. Not only are you, if you buy your drugs, not only are you spending whatever money you spent on the drugs, you're losing the opportunity cost of this reward in the contingency management. The problem is these rewards are tiny and drugs are inelastic, right? Now, drugs do have some elasticity, but only in the extreme kind of costs. And the original contingency management from the 1990s was a gift certificate to a $2 movie from Blockbuster. Like literally, if you didn't spend your tremendous amount of money you were spending on drugs, you got $2 additional to go watch a movie from Blockbuster, which was basically a in-person streaming house for those who are too young to know about videotapes and DVDs and stuff. So we realized, Paul Regier was a graduate student in my lab, and Paul and I realized that we could use demand curves to predict how good contingency management should do. So this is a demand curve from Bruner and Johnson. I believe these are cocaine users from the streets of Baltimore. And on the x-axis, we have the price of the commodity, and on the y-axis on the left, we have the units of commodity purchased, basically the demand. The black dots are an actual demand curve. And so let's imagine that the drugs are relatively cheap. And so we increase it by something like $10, which is not unreasonable for a modern contingency management. That's going to have a large shift on the x-axis. But if we're in the inelastic portion, it's not going to have a big effect. If the drugs are expensive and we're in the elastic portion, then yes, we have an effect, but it's small because we're in the large scale kind of components. Notice that the x-axis is log scale. So what we realized is we could compare predicted change against observed effect size. Of course, that's what all these studies are reporting, is the observed effect size. And basically, contingency management works better than expected. It should not work as well as it does. My colleague, Anthony DeFulio, who is a professor at Western Michigan University, contacted me about a year ago saying, this is really exciting. I want to follow up on this. And I was like, dude, the first thing we need to do is replicate it. And so we did. And so this is new studies, a paper that just got accepted in the Journal of Applied Behavioral Analysis like last week or the week before. And again, contingency management works better than it should. And the argument we're going to make is that it's shifting it from an is it worth it decision into a which one decision. And I want to point out that we've known for a long time that willing to pay and choose between can give you preference reversal. So Serge Ahmed, for example, who works with rats, he's the professor in the University of Bordeaux in France, has trained, for example, rats to push a lever to either get saccharin, which is sweet, or cocaine, which is, of course, a drug of abuse. And what they find is rats are much more willing to push the lever a lot for cocaine. That is, basically, they get to this point where you have to push the lever like hundreds of times to get your drug. And the question is, at what level of effort does the rat say, forget it, this isn't worth it? And so we can measure essentially the willingness to pay, or the utility of cocaine and saccharin. The utility of cocaine is larger than saccharin, so we can suggest that cocaine should be preferred to saccharin. They can then take these same rats, put them into a two-lever choice, where one lever gets you saccharin, the other gets you cocaine. And now rats actually choose the saccharin lever over the cocaine lever. So saccharin is preferred to cocaine, and we can infer that the utility of saccharin is greater than the utility of cocaine, and we have a problem, right? We have a preference reversal. I want to point out this is not new, because Liechtenstein and Slovak in 1960s went into gamblers, talked to gamblers in Las Vegas and measured gambles. And what they found is that the gamblers would sometimes say, sometimes they would say, which of these two gambles do you prefer? And sometimes they would say, how much are you willing to pay for one? And what they would find is preference reversals between a willing to pay choice and a choose between choice. And in fact, they point out that even when faced with this, when you point out to somebody, you've changed your mind here, they would shrug and say, yeah, but it feels right. So the argument is that what we're doing with contingency management is basically shifting people from, am I willing to pay this much for a drug, to would I rather have my drug or my gold star? And now we're in a different decision system. And that has consequences that we can talk about. Okay.
Do these rats know when they start, how many times they gotta push the lever to get this cocaine?
Yes.
Or is it a random?
No, it's the way this actually works, is a thing called progressive ratio. So you push it once, you get one hit. Then you have to push it twice to get a hit, then 4 times, then 8 times, then 16, and at some point they just are like, forget it. And you measure basically when they stop pushing the lever. That's the technical one. It's a standard model for measuring this. So the fact that deliberation depends on this imagination means that if we made the future more concrete, it would be easier to imagine. So Peters and Buchel in 2010 did this in the delay discounting space, where they said, which would you rather have, 20 euros immediately, or say 26 euros after 30 days? This is a classic delay discounting experimental measure. The difference is they also sometimes included a cue, such as when you're on vacation in Paris. And they had actually checked with these people. They briefed these people beforehand and gotten, so when they said vacation in Paris, it was a true, in 45 days, this person really was going to be on vacation in Paris. And what they found is the more that they imagined this outcome, and the more that it was easy to imagine this outcome, the slower the discounting rates, the more willing the people were to wait for that future. In fact, and Nancy Petrie has found that, she just passed away a few years ago, but she had run a lot of contingency management studies, and they worked for concrete outcomes and found that you could do it much more cheaply. That is, a contingency management for a concrete outcome worked better at a given price of the outcome than it did for money, for an equivalent amount of money. Basically, they would wait for less money, for cheaper things. You can also actually teach people how to think about that future. Warren Bickel has been doing a thing he calls episodic future thinking training, which literally teaches people how to imagine the future episodically. And what he found, again, Warren just also passed away, unfortunately, this summer, I think. The episodic future thinking training condition on the left here produced a slower discounting and a larger area under the curve, which is basically a measure of how slow the discounting rates are. So it slowed the discounting rates, made people more willing to wait for the future, and shifted the demand curves for, in this case, alcohol. Right? So in fact, understanding these mechanisms allows us to have concrete effects on things that are fundamentally economic, like delay discounting or demand curves. So the last thing I want to do, which I'll do relatively quickly, is just to point out we're starting to look into this exciting new project, looking at what is trust and community, and how does these things we've been talking about interact with that. And so there's two people I've been working with on this. One is a guy named Scott Allen, who's a graduate student at Cornell working on, of all things, physics education. And he was very interested in trust between students and faculty, but comes from both a military and a organizational psychology space. And then the other one is Antara Halder, who is a professor of law at Cambridge in the UK. And I've been working with her on questions of microfinance. She's an expert in microfinance. And what we realized is that trust is making yourself willing to be vulnerable to another. I'm going to make your decision change my outcome. But that's an action. I'm giving you that opportunity. I'm taking the action to let you now make that choice, which means we need to talk about our action systems. And it turns out there are different kinds of trust. There is instinctual trust, which comes from family and tribalism and is fundamentally not transactional. Fundamentally, an instinctual trust system is we are a family, we are a band of brothers. I will sacrifice everything for you and you will sacrifice everything for me. And we're not keeping track of who's doing what when. We also can talk about deliberate trust, which is explicitly based on logical prediction. And so this is going to be based on, it's going to be explicitly transactional, and it's going to depend on explicit expectations. I know you won't cheat me because if you cheat me, you'll be punished by this legal system that's over there. Now, if you go into the trust literature, you'll find often dual process separations, very much like the original dual process theories, that tend to kind of vaguely come close to what they would call affective and cognitive, which is kind of close to instinctual and deliberative. The instinctual deliberative lines turns out to give you a better separation and kind of more clear consequences. But deliberative systems will include things like diplomacy and trade and don't shoot down our medevac helicopters and we won't shoot down yours, right? Reciprocal deals. So when Scott Allen and I first started looking at this, I was like, but there are three systems. What's procedural trust? How do we get procedural trust? And we realized procedural trust makes sense when the world is so stable that the other person is just basically can become part of the world. And my favorite example is a quarterback throwing a pass to a wide receiver when the wide receiver has not started the slant. The wide receiver is going off to the left and the quarterback throws to the right, knowing that at some magic point, the wide receiver is going to turn and be at that point where the ball will hit at just the right moment. It also works for a surgical team where the doctor is watching a patient, reaches behind themselves and says scalpel, and a nurse puts a really sharp knife in their hand, and that doctor has never looked back because their eyes are on the patient. That's procedural trust. So when we're building community, whether we are building large construction projects, maintaining them for generations, preserving resources for future generations, responding to climate change, or in this case, as I said, we've started studying building successful microfinance enterprises. We need to build these based on these systems. We need to ask, how do the policies set in each of these things interact with these different decision systems? And this matches a lot of work that people like Ford Runge here, or Eleanor Ostrom, or Edna Ullman-Margalit have talked about in shifting things and how social norms and social codes shift things to change from competitive to cooperative worlds. And what we've discovered is basically you have to think about all three of these systems because the policies are creating and interacting with these systems. So I want to argue that this is a new microeconomic model with actual consequences, right? And so why do economists need to know the neuroscience? Because the neuroscience provides this microeconomic model with real policy consequences. And this is the microeconomic model. It has consequences both at small scale and at large scale. And this is the key that I think is there that needs to happen. Before I end, though, I want to take a quick moment and ask both for everybody who's here and everybody on Zoom, it would be really great for kind of hardcore real economists to start joining us. These are a few that come, but there needs to be more, and I think there's really a space for it. There is a Society for Neuroeconomics meeting. It happens every year. It's been going on for a while now. It alternates between Europe and the US. In October, it will be in Boston. So last October, you missed it. Sorry, it was in Portugal, which was lovely. But this year it'll be in Boston. And I would really like to encourage everybody to come and participate and see and bring that economic perspective in, because these are exactly the things that we're talking about. So I'm only a couple minutes over, but I'll stop there and hopefully there's some time for questions. Thank you very much. Jay.
How do you account for autistic people, bipolar people, ADHD people? What does that do to all of this?
So that's kind of the other side of the last 20 years of what I've been doing of neuroscience. So there is now a very large field called computational psychiatry, which turns out Minnesota is one of the main centers for. I was literally at our NeuroPrism, which is our computational psychiatry group, at 9 o'clock, and I came over from the West Bank to here. Basically, the answer is that what those things are doing is changing the mechanistic structure, which has computational consequences. When I do that talk, what I point out is that every decision is an interaction between an internal computational process and an external world. And basically what's happening is these conditions, these neurodiversity conditions that we are identifying as people with autism or schizophrenia or any of these other kinds of changes, are changing the way that that person, or I should say not necessarily changing, but that person is interacting with the world in a different way because it has changed the mechanistic consequence with a full computational, percolating up in the way that we're talking about consequences. Now, a lot of that psychiatry side is very interested in treatment. And the interesting issue there is it turns out this new, call it microeconomic model, but this neuroscience decision model is fundamental for how psychiatry is currently trying to do treatment. Both in terms of each of these systems learns in a different way, and so learning matters. Second, how changes, for example, in perception can have consequences that you can train and learn, you create new kinds of expertise. But also, if you understand how they interact with the world differently in the way like contingency management did, contingency management is not about changing the person's preferences. It's about changing the world structure that their preferences live in, right? They might still be craving drugs, but they're making different choices because you've created this change in the world. And so in psychiatry, a lot of the discussion now is about how do we change the world around us to accommodate people with these different issues. Right? So absolutely this whole logic, in fact, a lot of the logic that I'm bringing into economics and saying, like, economics, we're ready, was because psychiatry has spent about 20 years working with this kind of stuff and this kind of logic, and it's all been worked out there and can translate over in very nice ways. Right.
So in this new microeconomics, focusing on consumer behavior, so the
Right.
utility function, right? When you say there's these 4 different decision-making things, is that, when you're imagining the math of that, is that one utility function that's now very complicated? Is it like the dual processes where you have like competing things that turn on and off?
So one of the things, and actually Henry and I are working on this right now, to what extent is utility functions as understood by economists today in this old simple story of it's just a number? And to what extent is it actually a pretty complex math equation? So for example, you bring in people like Becker has history. Well, history means you have memory in your utility computation. You have, other people bring in context. And so you have contextual components, right? So I can imagine a utility function that says, U of cocaine, if one lever is what such and such, U of cocaine is if two levers such and such, right? To what extent, in the end, yes, if you if-then statements, you can do anything, right? If your utility function has an if-then statement, then yes, everything becomes turnable into this, right? But at that point, it's just a computational problem like neuroscience is doing, right? It doesn't really gain us much. The question that I think is not known yet is to what extent when these systems compete, if like your, one of the things we do with our rats all the time, we put them into a habit and then we change the world where they have to break that habit and do something else. These two systems are now competing. Is it that they're sitting there and system, the procedural system is saying, the utility of going left is 6 units, and the deliberative system says the utility of going right is 8 units, and that's what chooses? Is it that the one theory is that it's about uncertainty? The procedural system says, I think it's 6, but it's plus or minus some big range, and the deliberative system says, I'm sure if you go right, it's 5, choose that, right? To what extent it's something else, we don't know. But that is very much where neuroscience is happening, and there's a whole slew of labs, including mine, that are looking into that. But how these translate into utility in certain behaviors is very clear, right? So a lot of cases, like there's a big discussion about the trolley problem, right? About why is throwing the switch different from pushing somebody off a ledge? And the answer is because it accesses different decision systems, right? Why is willing to pay different from choose between? Because it accesses different decision systems. And so both from the put these systems in competition world, we can play games and it turns out explains a lot of the utility weirdnesses. But also the learning components, right? If you want to put in, like we were talking about, but Becker's, rational addiction model has a memory component in it because it changes after you've tried drugs. That memory component is going to matter. And it turns out the mechanisms make a difference, right? So I talked about how motivation matters. It turns out to really get an animal to, including a human, to not want food that they made them sick, they have to see it again and smell it. They don't have to eat it, but they have to basically smell it again, like, oh God, no, that's disgusting, right? And the reason for that is it turns out it's some subtleties about how the motivational systems in nucleus accumbens shell, I believe it is. I shouldn't say that, I should check, but we'll put that with a possible caveat. That's not the field I work directly in. But at least in ventral striatal areas and pallidum areas and stuff like that, those mechanistic of how neurons learn and how the neuroscience creates that consequence, right? And so why do you get preferences happening in these weird ways? Because of the mechanism in neuroscience. Go ahead. Okay. That's all we have time for, and I think we'll have to stop there. Thank you, everybody, and have a good day.